This video is to introduce the concept of ionization energy. To get to ionization energy, we begin with a diagram that I call the most probable distance diagram. We have talked about that, for example, in the atom nitrogen. Nitrogen has an electron configuration of 1s2, 2s2, 2p3, all right? And we know that what that means is that if the nitrogen nucleus is a tiny point in the middle containing its 7 protons and 6, 7, or 8 neutrons, we know that there's a region in space called the s orbital around that, where the 1s orbital, where the 2 electrons are found within that region. There's a region outside of that called the 2s orbital, where there are 2 more electrons found. There is a 2p orbital and another 2p orbital and another 2p orbital going back outside the plane of the paper, coming straight at you, but I can't draw that. So there are electrons contained within these regions, we know, all right, and we know that they're somewhere diffuse within there. We don't know exactly where they are at any given time. So we're going to simplify this picture because it's way too hard to think about this picture when we're thinking about the attractive force between particles, which is what we're going to do in just a moment. So we're going to imagine that there is some common distance that we would find the electrons at. So we're going to draw just a simple axis. This is going to be distance from the nucleus. All right, and at the origin we're going to put our nucleus, which contains 7 protons. And then we're going to say the 1s electrons are on average about, that far away from the nucleus. And these are the 1s electrons. The 2s electrons are quite a bit further, on average, again, from the nucleus, all right? And then the 3 electrons out in the 2p are just a smidge further, on average, away from the nucleus, all right? So this is, again, we know that really, in reality, those exist within orbitals that the electrons can exist anywhere within them, but what we're going to work from at this point is the notion that, well, there actually is a most probable distance that 1s electron is from the nucleus. It could be anywhere from here to here, we are going to accept that there's some, that we are making an approximation here by pretending that there is a usual or most common distance away from the nucleus. Same for the 2s's, same for the 3 2p's, all right? So that's for nitrogen. If we were to do another one for, say, sodium, sodium has the electron configuration 1s2, 2s2, 2p6, 3s1. We would graph its 11 protons being at the nucleus, and then we would have our distance from the nucleus axis here. And the 1s electrons would be the closest to the nucleus. The 2s would be the next closest. The 6 in the 2p are the next furthest. And then that lone 3s is way out here. Every time we jump from 1 to 2 to 3, we're going to see large changes in the distance, all right? We're going to use these most probable distance diagrams to explain a phenomenon known as first ionization energy. The first ionization energy is the amount of energy needed to remove the most easily removed electron from an atom, all right? And if we look at the periodic table, there is a distinct pattern to the way that ionization energies work. We're going to see that as we go to the right on the periodic table and up on the periodic table. Generally speaking, ionization energy is going to increase, all right? So the ionization energy in general, with a couple of exceptions that we'll deal with in a minute, are going to increase as you go to the right and as you go up on the periodic table. The highest ionization energy on the periodic table belongs to helium up here in the corner. That one is the highest ionization energy that you're going to find, all right? The lowest ionization energy would be down here with francium, all right? Now, we're going to use these most probable distance diagrams to start to make some understanding of the trends that we see. For now, we're just going to talk about the trend going to the right, all right? So let's compare boron and carbon. all right? So boron has the electron configuration 1s2, 2s2, 2p1. Carbon has the electron configuration 1s2, 2s2, 2p2. If we draw the most probable distance diagrams for those, boron is +5. Oops, got that one a little too far out, 2p. And then carbon would be +6 at the nucleus, 1s, 2s, 2p, all right? So if we go and look up the values for the first ionization energy, in other words, how much energy does it take to require to remove each of these electrons out here at the end? For boron, it's about 801 kilojoules per mole. And for carbon, it's about 1,087 kilojoules per mole. All right, so the question is, why does it take so much more energy to remove this electron from carbon than it does to remove that electron from boron? And the answer is, as is almost always going to be the case here, the answer is going to come from Coulomb's law. We know from Coulomb's law that the force is proportional to the charges over the distance squared, right? So the distance between the nucleus and that outermost electron, that's the distance we're interested in. How far apart are the charged particles here, the +6 nucleus, the -1 electron out here? So the distance for these two atoms between the nucleus and the 2p electrons is roughly the same, all right? They're almost the same because they're both in a 2p orbital. However, the carbon atom has the advantage that it has a +6 charge in its nucleus, whereas the boron atom has a +5 charge in its nucleus. So we're going to say the distances are about the same, all right? But for carbon, the charge product up here, the +6 times the -1, is larger than the +5 times the -1 is for boron. The bigger the charge, the greater the attractive force, and that's going to explain the higher ionization energy here for carbon, all right? This is always going to be the case except for one weirdo exception that we run into that we need to deal with, which is the exception dealing with the first paired electron in a row. And this is a really annoying exception, but it is something that you have to deal with, which is that if you compare nitrogen, 1s2, 2s2, 2p3, to oxygen, 1s2, 2s2, 2p4, all right, you see that the last electron for nitrogen requires about 1402 kilojoules per mole to remove, whereas for oxygen, it's only 1314. Normally you would think that the higher charge, normally we would draw our diagram here for nitrogen, it would have a +7 nucleus, 1s, 2s, 2p. For oxygen, it would have a +8, 1s, 2s, 2p. So normally you would think, oops, I drew too many electrons there. 1, 2, 3, 4, that's right. So normally you would think that the oxygen would have the greater ionization energy because you've got a +8. The distances from the nucleus to the outermost electron are about the same. However, if we draw the electron orbital diagram out for oxygen, and let's do that for both of them. So for nitrogen, you'd have 1s, 2s, 2p. Oh, goodness. What am I doing? There's only 3 electrons. Okay. And then for oxygen, and I'll draw this kind of goofy over here so that they are on top of each other. For oxygen, you have the 4 electrons. It turns out that this 4th electron here, this one here that got paired up, is actually a little easier to remove than you would normally think, okay? So this electron here is the one that gets removed. It gets removed, and it takes a little less energy than you would normally think to remove it, all right? This is referred to as pairing repulsion or pairing energy sometimes. The pairing repulsion here means that you have 2 electrons that are crammed into the same orbital. They're going to repel each other a little bit because they both have negative charges, All right, those negative charges are going to repel each other, repel each of those electrons, make it a little easier to remove this electron, essentially because it's not being attracted towards the nucleus as much as it would normally be because it's being partially repelled by that other electron. And that's going to explain this, this weird dip in electron, in the ionization energies here. When you go up to fluorine, it kind of, sort of goes back to normal. So with fluorine, which would be 1s, the next atom in the sequence here, 2p5, it's going to be back to 1681 kilojoules per mole. And so it's greater than oxygen. And the reason for it being greater is that that plus 9 charge in the nucleus is going to be a stronger attraction for that outermost electron than is the plus 8 in oxygen. They actually still suffer from pairing energy, the pairing repulsion, but it turns out that that it is, because both oxygen and fluorine are experiencing the pairing repulsion, then therefore we don't have to worry about it anymore. It's only the first time in a row, it's normally this P4 column in the periodic table where we have to deal with this stupid pairing repulsion problem. All right, so that's ionization energy across a row. Normally speaking, when we're talking about ionization energy, we're going to look at increases, generally speaking, going across the row, and it's basically because there's more protons in the nucleus. That's basically the reason. They're about the same distance. There are more protons in the nucleus as we go left to right. There's this weird thing that happens in the oxygen column that we have to worry about in the P4 column, where you end up with pairing repulsion that creates a little different effect, but that's really the only time we're going to have to worry about it. All right, now we're going to try to explain the second part of the ionization energy trend. We've seen that going left to right on the periodic table, we have more protons with electrons that are at about the same distance. So now we need to explain the trend about why does ionization energy increase going up the periodic table. Again, we're going to return to our most probable distance diagrams. Let's compare lithium with sodium. Those are right below each other on the periodic table. Lithium is here, sodium is here. Lithium has an electron configuration of 1s2, 2s1. Sodium has an electron configuration of 1s2, 2s2, 2p6, 3s1. So they're both s1 in their highest occupied orbital. So if we do the most probable distance diagrams for lithium, that would be a +3 in the nucleus, 2 electrons in the 1s, 1 in the 2s. And then for sodium, we would have 11 electrons in the, 11 protons in the nucleus for +11. 1s, 2s, 6, 2p, and then this lone 3s electron out here, all right? So the way we do this, this creates a problem because we need to be able to compare charge and distance every single time in Coulomb's law. Coulomb's law says that force is proportional to the product of the charges over the square of the distances. So we need to be able to have an apples to apples comparison here because we have a bigger charge in the nucleus for sodium, but a shorter distance from nucleus to an outermost electron for lithium. The way we do this is we create something we call the effective nuclear charge. In the effective nuclear charge picture, we combine the nucleus with all the core electrons. Remember that the core electrons are those that have these numbers out in front that are not the largest electrons in the present in the atom. Remember, the 3s electron here is known as the valence electron because that 3 is the largest of the orbital numbers that we encounter. And so what we're going to do is we're going to combine the nucleus and the core electrons all together into one imaginary charge centered still at the nucleus. So we have +11 on the nucleus, but we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. Those are a -10 charge altogether out here in the core. So the core plus the nucleus would have a total +1 charge, and then you still have this 3s electron out here all by itself, far away from the nucleus, all right? Let's do the same thing for lithium, all right? So for lithium, if we combine the 3+ and the core 1s electrons, we get a +1 charge there, and this 2s electron out here, all right? So now let's try to neaten this up a little bit and put it all on, put them on top. on top of each other. Now we have, for lithium, we have, instead of the the plus 3 nucleus and the 1s electrons, we have those all combined together in the effective nucleus. All right, we have this effective nucleus with a 2s electron out here. And then for sodium, we have a plus 1 effective nucleus again, but we have a 3s electron way out here. Now it's a pretty easy game with Coulomb's law to say, all right, we have the same charges, plus 1 and minus 1, in both cases. But for lithium, the electron is much closer to the nucleus, and therefore it's harder to separate that electron away from lithium than it is to separate this electron away from sodium. All right? So again, it's always charge and distance. Here the charges are the same, now we go to distance. The distance is greater for sodium, it's shorter for lithium. Shorter distances are greater attractive forces from Coulomb's law. And so we would say that lithium is going to have the greater first ionization energy, all right? So let's put this all back together. So now, if we look at our periodic table, all right, ionization energy increases going to the right and going up on the periodic table. It is greatest for helium. It is least for francium. All right, we know that going to the right, we have more protons within a row. We have more protons, and we have about the same distance between the nucleus and the electrons, and therefore the ionization energy increases because more protons means a greater charge on the nucleus. Going up, we have shorter distances between the nucleus and the outermost electron that's being removed. And we have the same effective nuclear charge within each column. As you work these out, within each column is always going to have the same effective nuclear charge. The only difference is helium, but that's a weird one. We'll deal with that later. But each column will have the same effective nuclear charge. Everything in the first column will have a plus 1 effective nuclear charge. Everything in the second column will have a plus 2 effective nuclear charge. When you get over here, except for helium, it's plus 8 for the noble gases, plus 7 for the halogens, fluorine, chlorine, etc. All right, and you can work the rest of those out for yourself, but this is going to be our overall trend. The only time we're going to have an exception to this is in that when we look at P3 going to P4, like we saw earlier with going from nitrogen to oxygen. There's a little dip from the pairing energy, but otherwise these two trends that are defined strictly by Coulomb's law are going to explain all the differences in ionization energies that we're going to encounter.